Evolution of astronomers continue to develop various observation and analysis methods to understand the formation, evolution, and diverse features of planets, particularly with the discovery of giant exoplanets. Techniques such as the transit method and Doppler spectroscopy, facilitated by space telescopes and ground-based observatories, provide valuable information about the sizes, masses, orbits, and atmospheric components of planets. The analysis of this data plays a critical role in determining the physical properties and chemical compositions of planets. For instance, the determination of specific gases in their atmospheres can offer significant clues about the temperature distribution, pressure regulation, and potential habitats for life. Furthermore, investigating geological processes and potential signs of life on the surfaces of planets is also of great importance. Future space missions will allow for closer examination of giant exoplanets and provide more precise data to determine their potential habitability. Additionally, the use of technologies such as artificial intelligence and machine learning can play a significant role in extracting meaningful information from large data sets and better understanding the characteristics of planets. In conclusion, the discovery and exploration of giant exoplanets offer an exciting opportunity to unravel the mysteries of the universe's depths and perhaps gain better insights into the evolution of life. Brown dwarfs are considered extremely intriguing and mysterious phenomena in astronomy. These objects can exhibit properties of both a typical star and a planet. Their atmospheres, composed of hydrogen and helium, can also be enriched with molecules such as water vapor, methane, and carbon monoxide. This presents an opportunity to investigate chemical signatures that carry traces of the planet formation process. Brown dwarfs are also known as substellar objects because they result from a failed stellar evolution. They typically form like stars, but when their hydrogen source is depleted and nuclear fusion ceases, they cool down and gases condense in their atmospheres. This positions them as a bridge between stars and planets. Research on brown dwarfs is expected to increase in the future, particularly with the use of next-generation space telescopes and observatories. The properties and diversity of these objects will be better understood, providing deeper insights into the overall structure of the universe. Furthermore, studying brown dwarfs to understand the process of planet formation and to seek answers to questions about the possible existence of life in the universe will continue to be a significant research area in planets form and evolve. Additionally, despite these dwarfs having temperatures of only around 100, these objects can serve as a bridge between stars and planets. Their atmospheres, composed of hydrogen and helium, can also be enriched with molecules such as water vapor, methane, and carbon monoxide. The presence of these components in their atmospheres can help us understand different stages of planet formation and shed light on the early stages of the universe. The examination of cold brown dwarfs by the JWST can be considered a milestone in astronomy. The advanced technology of this telescope provides the ability to observe unprecedented details and contributes greatly to our knowledge in the field of astronomy. In the future, JWST is expected to continue these types of research and discover more cold brown dwarfs. In conclusion, the research on cold brown dwarfs by JWST plays a significant role in understanding the process of planet formation and unraveling the mysteries of the universe. The continuation of these studies will further enhance discoveries and knowledge in the field of astronomy. Isotopes are commonly found in nature in varying proportions, forming the natural composition of an element with different isotopes of various subatomic particles. For instance, carbon-12 is the most common isotope of carbon, but radioactive isotopes like carbon-14 also exist in nature. The different masses of isotopes can cause different behaviors of the various isotopes of an element in chemical reactions. Isotopologues deal with atoms within molecules that have different isotopes. They particularly focus on how isotopic ratios affect the chemical reactions and physical properties of molecules. This can help us understand the origin, formation, and transformation of a molecule. Isotopes and isotopologues play significant roles in planetary science and astrophysics. For example, isotopic analyses are commonly used to understand the chemical compositions of planets, asteroids, and comets. Additionally, in the search for extraterrestrial life, isotopes can be an important tool in evaluating the habitability potential of a planet or celestial body. In the future, further advancements in isotope and isotopologue research are expected. These studies could provide a deeper understanding of the structure, origin, and evolution of the universe. Additionally, a better understanding of the formation processes of planets and celestial bodies could help us comprehend humanity's place and origin in the universe. This additional information could help provide a more comprehensive understanding of isotopes and isotopologues. If there are any specific topics or details you'd like to explore further, we can focus on those as well. Ammonia isotopologues also play a significant role in environmental sciences. Specifically, the release and cycling of ammonia from various sources into the atmosphere can affect issues such as climate change and air quality. Therefore, isotopic analyses of ammonia can be an important tool to understand the effects of environmental factors and determine the origin of atmospheric ammonia. Furthermore, there is potential for the use of ammonia isotopologues in agricultural applications. Fertilizers and organic wastes used in agricultural fields can contribute to ammonia emissions and environmental impacts. Isotopic analyses can aid in monitoring and managing these sources, thereby contributing to the development of sustainable agricultural practices. In the future, advancements in technology and methodologies are expected to further advance ammonia isotopologues. These developments could enable more comprehensive research in fields such as planetary science, astrobiology, environmental science, and agriculture. Additionally, such research could help us better understand the complex nature of our planet and universe and develop measures for environmental sustainability. In conclusion, ammonia isotopologues represent an important research area with diverse applications in various scientific fields. Further advancements in this area could be critical for advancements in science and technology, as well as for the sustainability of our planet and life. The isotopes in the atmospheres of the planets in the solar system can provide valuable clues about the formation process of these planets. Understanding how different isotopic ratios form during the formation of the Sun and the planets is crucial for understanding the origin and evolution of the planets. For example, isotopes found in Earth's atmosphere can help us understand the effects of early meteorite bombardments and the origin of Earth. However, studying the isotopes in the atmospheres of outer planets is more challenging due to the distant distances to these planets and limitations in observation techniques. Therefore, new technologies and telescopes are required for space observations. The James Webb Space Telescope, JWST, has become an extremely important tool for studying the atmospheres of outer planets. With its sharp eyes and sensitive equipment, JWST has the ability to detect and analyze isotopes in planet atmospheres. This could help us better understand the chemical composition and formation processes of outer planets. In particular, the ammonia isotopologues in the atmospheres of brown dwarfs are one of the recent discoveries of JWST. These isotope analyses offer the opportunity to examine the chemical composition of outer planet atmospheres in more detail, which could provide a deeper understanding of the nature and formation of planets beyond the solar system. In the future, the development of telescopes like JWST and advancements in space observation technology could allow us to study the isotopes in the atmospheres of outer planets in more detail. Such research could lead to significant advancements in planetary science and astrobiology and help us develop a more comprehensive understanding of the nature of the universe. The discovery of ammonia isotopologues in the atmosphere of the cold brown dwarf WISE J1828 was made using the Mid-Infrared Instrument, MIRE, of the James Webb Space Telescope, JWST. This discovery marks a significant milestone in astronomy and provides an important step towards understanding the process of planet formation. The brown dwarf WISE J1828 is located at a considerable distance from the solar system, requiring the use of state-of-the-art telescopes like JWST for its atmosphere's examination. The detection of ammonia isotopologues in the atmosphere of WISE J1828 provides valuable information about planet formation and chemical evolution. In particular, the low temperature of the brown dwarf allows for clearer detection of spectral signatures of molecules. This enhances JWST's ability to examine atmospheric composition in more detail and provides a deeper understanding of planet formation and evolution. It's in astrobiology, opening new doors to unravel the mysteries of the universe. Nitrogen isotopes provide valuable information about the formation conditions, chemical composition, and even the evolution of planets. First and foremost, the abundance of ammonia in the atmospheres of giant planets in the solar system emphasizes the importance of ammonia isotopologues. The ratios of these isotopes provide crucial clues about the formation processes of planets. Specifically, examining the ammonia isotopic ratios in the atmospheres of outer planets, Jupiter, Saturn, Uranus, and Neptune, helps us understand how these planets formed and how their chemical compositions evolved. Analyses of ammonia isotopologues also provide important information about the atmospheric dynamics and chemical evolution processes of outer planets. In particular, the variability of ammonia isotopic ratios in the atmospheres of outer planets can reveal the complexity and diversity of their formation processes. This is crucial for developing planet formation models and understanding the overall evolutionary process of the universe. Furthermore, the importance of ammonia isotopologues in the field of astrobiology should not be overlooked. Ammonia can provide clues about the existence or potential of life. Specifically, examining the ammonia isotopic ratios on outer planets could be an important tool for determining the potential existence of life on these planets. In conclusion, the analysis of ammonia isotopologues represents an important research area in planetary science and astrobiology. Studying these isotopes can help us gain a comprehensive understanding of planet formation, evolution, and even the existence of life. Therefore, there should be a greater focus on this area in future research endeavors. The relationship between planet formation and isotopes is indeed a subject of great interest in the fields of astrophysics and astronomy. When combined with laboratory experiments and observations from space telescopes, these data can shed light on the details of planet formation. In particular, the data we obtain about the isotopic composition of the planets in the solar system can help us better understand the birth of outer planets. The isotopic compositions of the planets in the solar system reflect the formation processes and chemical evolution of the Sun and other stars. This data plays a significant role in determining whether outer planets have similar or different isotopic compositions. However, further research in this field is needed. In particular, it is important to more comprehensively study and analyze the isotopic compositions of outer planets. This could contribute to the development of planet formation models, a better understanding of the formation conditions of planets outside the solar system, and the explanation of the overall evolutionary process of the universe. In the future, with technological and methodological advancements in astrophysics laboratories and observations from space telescopes, it will be possible to examine the relationship between planet formation and isotopes in more depth. Such research could help us find answers to fundamental questions in planetary science, astrobiology, and the overall structure of the universe. Gas giants like Jupiter and Saturn are among the largest and most prominent planets in the solar system. By examining their atmospheres, particularly in terms of isotopic ratios, we can gain insights into the planet formation process and the early stages of the solar system. The isotopic ratios in Jupiter's atmosphere, especially those of elements like hydrogen and helium, are noteworthy. These isotopic ratios contribute significantly to understanding the conditions and material mix in the early stages of the solar system. For example, the isotopic ratios in Jupiter's atmosphere can provide clues about the distribution of material within the protosolar disk of the Sun. This, in turn, can help us better understand how the solar system formed and evolved. Similar isotopic measurements have also been made in the atmospheres of other gas giants like Saturn. These measurements can help us better understand the complexity and diversity of the planet formation process. Additionally, conducting similar isotopic measurements in outer planets can provide important information about the formation conditions and chemical composition of planets outside the solar system. Therefore, studying the isotopic ratios in the atmospheres of gas giants like Jupiter and Saturn provides valuable information about planet formation and evolution. In the future, further deepening these observations and analyses can greatly contribute to our understanding of the formation processes of the solar system and other star systems. The importance of isotopic ratios lies in providing valuable clues about planet formation and evolution. Different isotopic ratios allow us to trace the regions where planets formed and their migration paths. This helps us understand the formation of the solar system and other star systems, and unravel the overall evolutionary process of the universe. In particular, significant differences in isotopic ratios have been found among objects in the inner and outer solar system. These differences provide important information about the formation and evolution process of planets and small objects in different regions of the solar system. For example, the isotopic ratios of planets in the inner solar system provide information about the distribution of material within the protosolar disk of the Sun and the planet formation process. On the other hand, the isotopic ratios of objects in the outer solar system can reflect the material conditions and migration paths in colder and more distant regions. These differences in isotopic ratios help us understand the origins and evolution of planets and small objects. Additionally, they highlight the complexity of the formation process and chemical evolution of the solar system. In conclusion, studying isotopic ratios helps us understand the formation of the solar system and other star systems and unravel the overall evolutionary process of the universe. In the future, further deepening research in this field can lead to significant advancements in planetary science and astrobiology. The cores of planets and their magnetic fields can be examined through isotopic analysis. These analyses help us understand the formation processes of planets, their core structures, atmospheric evolution, and magnetic fields. Isotopic analyses play a critical role in understanding a planet's history and developmental processes. For example, isotopic analyses conducted on Mars have provided strong evidence of water presence in the planet's past. These analyses reveal the conditions of the Martian atmosphere and surface formation processes, shedding light on the past conditions conducive to water existence. Similarly, isotopic analyses of other planets can illuminate their geological and climatic histories. Isotopic analyses conducted on distant exoplanets can provide clues about the presence of water or other vital components on their surfaces or atmospheres. Particularly, the isotopic composition of water offers significant insights into a planet's formation conditions and evolution. These analyses can help determine the habitability potential of planets and aid in the search for other forms of life. In conclusion, isotopic analyses represent a significant research area in planetary science and astrobiology. They provide valuable information about the formation, evolution, and habitability potential of planets, guiding the planning of future space missions. The suggestion that traces of life could be found in the atmospheres of giant exoplanets is indeed an exciting prospect. These massive planets might create an environment conducive to life under extraordinary conditions. In particular, the chemical compositions and isotopic ratios found in the atmospheres of giant exoplanets can provide valuable clues about the presence or potential for life. For example, the discovery of molecules such as water vapor, methane, and ammonia in their atmospheres could suggest the presence of life on these planets. To gain a deeper understanding of the existence or potential for life on planets, future research will need to more thoroughly examine the atmospheres of these giant exoplanets. This could become a significant goal for future generation space telescopes and space missions, such as JWST. This assumption could serve as inspiration for future research and could change our views on the prevalence of life in the universe. If traces of life are found on giant exoplanets, it could increase our awareness of how common life may be in the universe and lead to a reassessment of humanity's place in the grand scale of the cosmos. Therefore, research into the possibility of life in the atmospheres of giant exoplanets could become one of the significant research areas in planetary science and astrobiology in the future. Such studies could provide a deep understanding of humanity's place in the universe and the evolution of life. These exciting discoveries shed light on the ambitious and thrilling future goals of scientists. Understanding the formation processes of planets, exploring the existence of life in the universe, and perhaps discovering other life forms are aspirations that drive us towards a deeper understanding. The formation processes of planets are crucial factors that determine the likelihood and potential development of life in the universe. Enhancing our understanding of planet formation processes leads to significant advancements in planetary science and helps us identify the conditions for the formation of habitable planets. Exploring the existence of life in the universe is one of the fundamental goals of astrobiology. To achieve this goal, it is necessary to investigate traces of life on planets, examine the chemical compositions in planet inclusion. The future goals of scientists aim to deepen and expand our understanding of planetary technological advancements. This can help us better understand and evaluate humanity's place in the universe and our own existence. Looking ahead, the construction of larger and more sensitive telescopes and the planning of new space missions are crucial. Particularly, the aerial, atmospheric remote sensing infrared exoplanet large survey mission developed by the European Space Agency, ESA, represents a significant step forward. The aerial mission, scheduled for launch in 2028, aims to examine the atmospheric compositions of over 1,000 exoplanets. This mission could revolutionize isotopic analysis and reveal the detailed chemical compositions of distant planets. Ariel will conduct spectral observations at different wavelengths to determine the composition of gases and temperature profiles in exoplanet atmospheres. These observations can provide significant insights into the formation processes and evolution of planets. In addition to the aerial mission, other large telescopes and space missions also hold great potential for future research. For example, next-generation space telescopes like the James Webb Space Telescope, JWST, can be utilized to examine exoplanet atmospheres and isotopic compositions in more detail. Next-generation telescopes and space missions could lead to significant advancements in planetary science and astrobiology. These missions can provide a deeper understanding of the formation, evolution, and potential for life on planets, and offer crucial clues about the prevalence of life in the universe. In conclusion, new generation telescopes and space missions like Ariel serve as important research tools in planetary science and astrobiology. These missions present exciting opportunities to explore the existence of life and better understand the formation processes of planets. See you later.